Hey, what's happening here? Lots of patterns of numbers, and you can see there's some sequences here of numbers in different rows and stuff. And this is the Binomial Theorem introduction, and what we've got floating around here is a version or various versions of what's called Pascal's Triangle from a French mathematician, Blaise Pascal. And around the 1600s, he had a look at the patterns in these triangles that he's created here. And however, well before that, the Chinese knew about it. Have a look here. How universal is the mathematics language there? And that was in around the 1300s, so you might like to read that. The Chinese, excuse me, were looking at patterns in this triangle before Pascal. But I guess Pascal looked at more patterns overall, the different patterns. So we're going to have a look at what has this got to do with binomial theorem, the binomial theorem, because these are all look like sequences. Each one of these is a certain sequence or pattern of numbers, and there's some interesting connections here, and it looks like the sequence is symmetrical. The triangle has equal sides there, and what's this going on up here? This looks like powers of 2. 2 to the naught, 2 to the 1, 2 squared. Lots of different patterns in this triangle. Anyway, it's called Pascal's Triangle. That's enough of that. And we want to know what's its connection to the binomial theorem. Well, hang on. Do you know what the binomial theorem is, or do you know what a binomial is? Come on down and let's have a look. The binomial theorem. Well, bi means 2. There's lots of words with that prefix. Bicycle, 2 wheels. Bilingual, can speak 2 languages. So what do you reckon binomial means? 2 numbers. And what we're going to do is we're going to look at 2 numbers, x plus y, and we're going to raise x plus y to any power, like x plus y to the n. Like you already know that, I hope. X plus y squared is the first one squared plus twice the second one, twice the product plus the second one squared. And I wonder if you're good enough to get x plus y cubed. Well, wouldn't you just take this doofy here and multiply it, that's the square, and multiply it by another x plus y. You could actually do it, but hey, pretty boring stuff. Well, that's what we're going to investigate now. Is there a trend as you keep raising this binomial expression to higher and higher powers? Is there a theorem? Is there a rule? Is there a pattern? I bet you can hardly wait. Well, anyway, come down here and let's have a look at the pattern. And we're taking screen clippings here from Pearson's new textbook for the new IB course, first examinations in 2014. So here we go, x plus y to the naught. Anything except 0 raised to the naught is 1. Then x plus y to the 1 is just x plus y. X plus y squared, just did it. Now, if you do multiply this one by another x plus y, and it's going to be a big foil, isn't it, where you're expanding brackets, you get this pattern. And then if you multiply it again by another x plus y, you get this, and so on. So here, Pearson's have put these terms in a certain order, and let's have a look at that order, always starting off with the highest power of x. And if we looked at it, then you can see there's a pattern in the way those terms are written. So let's come down and have a little bit further look at this. And here we have some of those diagrams from before. And can you see here that if you write the terms with the highest power of x, come over here, and then just the next power of x is just x, and then no x's in the term at all, then the numbers of these, 1, 2, 1, occur in the triangle here, 1, 2, 1. And then the next set of numbers, here you've got 1x cubed, 3x squared y, 3xy squared, and 1y cubed. The numbers are there. So can you see that this is called Pascal's Triangle, and it contains the coefficients of the terms in the binomial expansion, the coefficients of terms, how many of each one you'll get. So here's another representation here without little boxes, and I think it's showing you here that how do you go from one row to the next of Pascal's triangle? Well, you could add those two up to get 3, and if you add these two up to get the 3, then 3 and 3 is 6. 1 and 3 is 4. Can you see it? Summing 2 here gives the next entry in the next row. So what do you reckon would be in this posse down here? That would be 15. And here would be 15, and so on. No, sorry, I've made a mistake there, haven't I? That's 20. The next 15 is over on the other side, so that's 20, and then this would be 15. So that's one of the patterns Pascal was actually looking at, how to generate further rows of the triangle. But the connection is over here, where if you have x plus y to the 4th, you would be looking at this row here, and there'd be 1 of the highest power term, 4x cubed y, and then 6x squared y squared, 4xy cubed, and 1y to the 4th. So this is a good tricky way of quickly working out the number of terms in a binomial expansion, particularly when you get up here to higher powers there. So can we see a system then of getting it right? Well, here we have it here. Let's do x plus y to the 7th. Now, have you seen that the pattern is, if it's x to the 7th, the next term is x to the 6th and y to the 1. Hey, the sum of those powers is always 7. Then the next term would be x to the 5th, y squared. The sum of those powers is always 7. And then x to the 4th, y cubed. The sum of those powers, always 7. So x is dropping down by 1 and y is coming up by 1, and the sum of the powers is always 7. So what's the next term? X squared's dropped down by 1, y's grown by 1 to y to the 5th. Sum is 7. And you keep the pattern going until there is no x term and they're all y's. So that actually is a system. That system will generate all possible terms. System to detect all possible terms in the binomial expansion. Okay, so we put them in that order. And if we do, these numbers here, okay, this number, and this number, are all going to be able to be found from Pascal's triangle. And later on, there's excitement. We're going to see why that works, why the triangle actually works. But at the moment, Pascal discovered that when he broke down all the terms, the coefficients, or the number in front of each type of term, came from Pascal's triangle. From that triangle you could work out how many terms, how many of each particular structured term you had. Okay, so can we go and do it? Let's have a look. Well, here we have Pascal's triangle next to this, the same expansion. So where will we find the expansion of x plus y to the 7th? Well, here it is here. So we could call this term n equals 0, n equals 1, y, because that's x plus 1 to the x plus y to the 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, n equals 7. So this is the row we want. Let's pick out the first number is 1. We got 1 of them. Then the next is 7. So we got 7 over here. And then there's 21. So we got 21 of them. And then 34. 35 in this one. We got 35 of that type of term, 35 of the next type of term, and then 21 of the next type of term, and so on. You must keep the terms in that particular pattern though. Highest power of x. Okay, going down by 1 to no x term, and highest power of y. Okay, so Pascal's triangle is very closely linked to that expansion, that binomial expansion, x plus y to the n. Okay. Or to any other binomial application. Now, there is probability, of course, where the sum of, let's say there's a binomial experiment in probability, and bi means 2, so that could be an experiment where there were 2 outcomes. Then you would have 2 values, p plus q, which would be the 2 probability of the 2 outcomes. We might call it success and failure, and you might be interested in raising that to a power, okay, and seeing all the possible combinations of those 2 outcomes. So binomial theorem is applied to expansions. Expanding terms come over here like this, but it's also applicable to the binomial probability distribution. So we'll have a look at that a bit later on. Okay, come on down and let's have a look at a bit of a summary here. So here are the first 6 expansions of that binomial expression x plus y, and here is the way in which we can actually find the number of each of those terms. But what we've got now is, let's have a look at some properties and see if we can track these through. There are n plus 1 terms in the expansion of x plus y to the n. What does that mean? Well, here, if the power is 1, you'll have 2 terms. 1 more. If the power is 2, there'll be 3 terms. If the power is 3, there'll be 4 terms, and so on. So down to the power of 6, there are actually 7 terms here. Okay, and the degree of each term is n means that, easier said, the sum of the powers in each term is n. The n degree, or if you like to put it that way, but the sum of the powers in each term is n. So what does that mean? Well, it's x to the 6, and then 5 plus 1, sum of the powers is 6, 4 plus 2, sum of the powers is 6, 3 plus 3, you can see the idea. The powers on x begin with n and decrease to 0. That is, over here, highest power of x, and then going down to no power of x and highest power of y. The powers on y begin with 0 and increase to n. Just like we were saying, it's trying to get it all together here now, and the coefficients are symmetric. They've got a symmetry here, and that's what this is saying. See that line down there? On either side of that, there is symmetry. So you've got the coefficients coming from Pascal's triangle, and then you've also got the pattern of terms. Now, it only works if you keep that pattern of terms. You can't shuffle them around, otherwise you lose the pattern of the sequences in Pascal's triangle, and we're going to investigate that in this presentation. Let's have a look at how we can use some of this now. So use Pascal's triangle to expand 2k, take 3 to the 5th. Now that's a little bit different, because instead of just x and y, we've got the first term is 2k, and the second term is neg 3. All of neg 3, not just 3. Okay, so here we go. Using the 5th row of Pascal's triangle, what would we have? We'd have these red numbers, 1, 5, 10, 10, 5, and 1. But you must have the terms in the right order. So you start off with the first term, which is 2k, to the highest power, that's 5th. then 2k to the 1 less power, and the neg 3 comes in, neg 3 to the 1. And then 2k to the 1 less power, it's to the 3, and neg 3 to the 2. So that way the sum of the powers will always be 5. One's going up and the other's going down. So 2k is now down to 2, and neg 3 is up to 3. 2k goes to 1, neg 3 goes to 4, and the last term then is the neg 3 has been raised to the highest power. Now let's get rid of all the mess I've created there and say, what does that mean about the expansion if we simplify the terms? Well, let's look at the first one. 2k to the 5th is 2 to the 5th, 32k to the 5th. And now neg 3 here is going to make this term negative. So what are the constants? It's 5 times 2 to the 4th. Don't forget the 2 has to be raised to the 4th. That's 16, that's 80. Times neg 3 is neg 240. So we're going to simplify some of these terms now. And then there's k to the 4th. Let's look at this one. 2k cubed is 8k cubed by 10 is 80, and neg 3 squared is positive 9, so that's 720k cubed. So you've got to keep your wits about you here. Everything in the brackets, including the negative sign, has to be raised to that power. So the next term then, let's just get rid of that. The next term is 2k all squared. So that's 2 squared is 4k squared, by 10 is 40k squared, and then times by neg 3 cubed is neg 27. So this number here is 40 by neg 27. Therefore, it's going to have a negative sign. Can you see that the signs are going to alternate? Because if you raise a negative to an odd power, you'll get a negative. But if you raise a negative to an even power, you'll get a positive. So let's do this one. 5 by 2, no power there for that. That's 10 by neg 3 to the 4th is positive 81. This is a negative raised to an even power is positive 81. Times 10 is positive 810k. And then at the end here, neg 3 to the 5th is going to be a negative number, and that's going to be 243. So that's our last term there. So that's a fairly complicated one. So what I've done with Pearson's is to split their exercise from the end of this section into relevant sections. So now I want you to try and put the terms in the right order. Remember the rule, you start off with the highest power of the first one in the bracket and no power for the second term, and then the power of the first term decreases and the power of the second term increases by 1 each time. So you must get what? The pattern. Hang on, here, let's just go back then. Okay, so just remembering those two there. So again, just repeating that, the pattern of terms, and then we want the coefficients from Pascal's Triangle. Okay, so we've got to get those terms in the right order. All right. I want you to have a go at those. Pause it now and I'll show you the solutions. So later on, come down with me and let's have a look at those solutions. Question 1. Just check your total solutions there. Okay, let's move on and develop this a little. This is going to be interesting. So here we are. Pascal's Triangle is an easy and useful tool in finding the coefficients of the binomial. But what if you went up to 20? That means you'd have to do 20 rows of Pascal's Triangle. That could be very, very time consuming, because you just got to put one row after the other. So therefore, can we do it a little bit more easily than that? Is there a way of getting the coefficients, the number in front of each term, the coefficients without Pascal's triangle. Is that possible? Okay, so what are the coefficients? How could they be calculated? Okay, how could they be calculated? All right, well, we could, for example, use the calculator. It's actually a symbol for these coefficients, which is NR. They're calling this a binomial coefficient, but actually its mathematical roots are broader than that. It's actually called CNR, which is equivalent to the combination of n items taken at a time. Okay, so this is beyond this course to understand combinatorial theory, but I think it's important that you realise that's where it comes from. And what we're looking at, really speaking, is if we had, let's stay with x plus y, if we had x plus y by x plus y by x plus y, etc., let's do those three, that's x plus y cubed, isn't it? If we did that, when we're trying to work out a particular term, let's say we're working out the x squared y term, how many would we have? We want to know how many ways from 3 brackets can you choose 2 x's. And the other one would be a y, because you know each term has to be multiplied by a term from each other bracket, like an extended FOIL, first out is in as last. So from 3 brackets, we want to pick out 2 x's and a y. So that is the combination of 3 brackets taken. How many times can we pull out a y? Well, C3, 1. And the other 2 brackets would be the x. We can put it like that. And then the next term, xy squared, would be the number of ways from 3 brackets we can choose 2 y's. So the CNR notation is a notation representing the combination of n items taken r at a time. How many ways can you choose r objects from n? And then that is actually abbreviated to this here, and we could call that the combination, the binomial coefficient, if you like. And on the calculator, here we are, it's written as NCR. So I want to show you now how to use the Casio in doing this. So if you go to run mode, you'd have this window here, and if you then hit options, okay, so the option key is here, hit options, and you get this window. And then what we want to do is we have to go to the next window, so hit F6. If you go to the next window, you get this, and you're wanting probability here, because as I mentioned, the binomial pattern of terms also occurs in the binomial probability distribution. So if we choose that by hitting F3, we get this window, and there it is there. NCR, the combination of n items taken r at a time. Okay, and so we're using that to choose how many ways we can create different terms from the binomial expansion, choosing a particular x or y from a particular number of brackets. So there's a little bit of a background. We're going to go on with that a bit now. Okay, so the binomial coefficient, that's CNR, or it's equivalent to that without the R, combinatorial theory here. And this is beyond this course, but that symbol is defined as n factorial over r factorial by n take r factorial. Oh, what's that exclamation mark mean? It means n factorial. So let's go down and define that, because this is something new in the course, in the standard level course of the IB, in this particular course compared to others. So let's investigate this now. So factorial notation, it's called n factorial, n exclamation mark, and n factorial means every number from n down to 1 has got to be a factor. It's all times together. So 1 by 2 right up to n is called n factorial. It also happens that 0 factorial is 1. We define 0 factorial as 1. Now, that's a little bit hard to understand, but we might have a go at it. Let's have a look at this over here. Let's say we've got, well, it might be a bit hard, Cn naught, and we said that was n factorial over naught factorial by n take naught factorial, using the formula here, right, for the general CNR. So if you put naught there, now Cn naught means in how many ways can you choose no items from n? In other words, you're keeping the whole lot. So the answer then must be 1, mustn't it? The number of ways you can choose 0 objects from n. Only one way, you're actually choosing none. So this answer should be 1. Well, let's have a look at it. We've got n factorial over naught factorial by n factorial. Hey, they will cancel. So that's 1. For this bottom line to stay 1, it implies 0 factorial must equal 1. So we get that interesting result, because you can't actually use this definition to define 0 factorial. Multiply by every number between itself and 1. Okay, so we can't actually use that. We've got to come at it from this point of view here. All right, let's go down and see if we can do some examples. All right, so let's go across here and have a look. Find the value of C73 using the definition 7 factorial over 7 take 3 factorial and by 3 factorial. Now factorial, let's write them all out. 1 through 7 times together, 3 factorial, 1, 2, 3, 4 factorial is that, and then cancel some stuff. Okay, so remember the dot on the line in Pearson's means multiplication. And so if we then have a look here at the next one, C74, let's just pause that there. So having a look at that now, the next one, C74, 7 factorial over 4 factorial by 7 take 4 factorial, 7 factorial over 4 factorial by 3 factorial. 7 factorial is 1 through 7 all times together. 4 factorial is 1 through 4 times together. And 7 take 4 is 3 factorial. 1, 2, 3 multiplied together. And if you cancel those, oh, we're getting the same answer. I think this is reminding us of the symmetry of Pascal's triangle. Okay, because what we're going to find, and you can check this other one out, 7 factorial over naught factorial and so on, that's 1 over 1. That's one we just did. 7 factorial over naught factorial is 1. So those values now are being calculated instead of drawing up Pascal's triangle. Do you see it down here? That's what we're saying. Each of the entries, that is row n equals 0, n equals 1, n equals 2, n equals 3, etc. Each of these are combination expressions. Cn0, Cn1, Cn2. Notice you start down here with Cn0. Okay, so and then because that's the first one, you're choosing no y's out of the brackets if you like. So there's only one way of doing that. Let's have a look at these. It looks like that's a row of Pascal's triangle, isn't it? C6 on the outside, C6 1, C6 2, C6 3, etc. If you were to work those out, then you would have these numbers here. And these are the 6th row of Pascal's triangle. Now, Pearson's has written Pascal's triangle like this. I'd like you to write it more in triangular form here. as a isosceles triangle, if you like. But this is okay too. You can see that all those numbers form part of Pascal's triangle, and they are combination coefficients, so CNR, or using this. Okay, can you do some? So I've chosen the ones like this from Pearson's, and they want you to evaluate these expressions. So this is timesing the two together here. All right, pause it and see how you go with all of that. And the idea is that you're going to evaluate the NCR expression using this. You could check it on the calculator, but using that symbol and cancelling. All right, have a go. Here are the solutions. Okay, so have a look at those. We just go back a little bit there, I think. Part C was timesing. Yep, that's all right. Very good. All right, have a go. Mark your work. Let's go on. So here's another example. Example 23. Calculate CNR take 1 plus CNR. Well, fairly complicated here. N factorial over R take 1 factorial, then take the 2 away. Lots of symbols. N factorial over R factorial, take the 2 away. Now, here they've multiplied top and bottom by R. Why? Because that then is going to give you R factorial. Okay, and over here if we multiply by n take R plus 1, that will give you n take R plus 1 factorial. Fairly complicated here. And so what does that mean? Then you've got them all over R factorial, n take R factorial. So it's this term plus this term all over it. Okay, so if you add that up, what have you got? n factorial out the front, and in the bracket R plus n take here R, and then plus n take R plus 1 in the bracket. And so if you work this out, they cancel. That's n plus 1 by n factorial over this. So that's n plus 1 factorial by n plus 1 take R factorial. Oh, that is the definition of n plus 1 factorial CNR, sorry, C n plus 1 R, because it's n plus 1 factorial over R factorial times the difference. Fairly complicated proof. What have we just done though? Here it says you'll be able to provide a reason for the steps after you do the exercise. What we've just done is, let's take this one here. Let's say we've got, this is C3 R take 1, that's C3 R1, and this is, well, let's do it as it stands there. Here, n is 3, both cases. If this is R, this is R take 1. We've just shown when you add them, you get the entry CNR. We've just proven why Pascal's triangle works. Because Pascal's triangle are these expressions, combination expressions. And why does the triangle work? Because when you take an entry to the left and add the next R to it, okay, and go to the next term and add them up, you get equivalent to, oops, I made a mistake there, n plus 1, the next one down in that rth position. So actually showing that the sum of two entries in one row gives you the middle entry in the next. So this is the proof of, this explains why Pascal's triangle works, if you like. How do you construct it? Why does it work from a combination point of view, or a coefficient point of view? All right, come down and let's use the binomial theorem. The binomial theorem is talking about how to get the terms of x plus y to the n. So we start off with a higher power of x, and it's Cn naught. Then reduce the power by 1, increase the y power, and the next one is Cn1. That's the number of that particular term. Decrease the power of x by another one, increase the y, and that's the number of terms of that type. So we don't need Pascal's notation. Now we use the sigma notation to indicate you're adding up all the terms in a binomial. So you're going to start off at I is 0 and go to n. And the coefficient is Cni. And then you start off with the highest power of x, which is n take I, and I starts at 0. So that'll be x to the n take 0, which is x to the n, and then y to the I. So this is a way of ensuring the x term power goes down, the y term power goes up. The x term starts at x to the n and y to the 0, that's why y is I. We're starting at I is 0, and we go right through until x is 0 and y goes to n. Okay, so let's see if we can use that sort of pattern. It's good to understand this, but I think writing it down is not as important as being able to apply it. Let's see if we can apply it in these problems here. X plus y to the 7th. Start off with x to the 7th and no y term. And it's C7 0. And then x goes to the 6th and 7 take 1, or to the 6th power, and y comes into the 1, and it's C7 1. How many terms have we got? Then you reduce the x power by another one, so it's down to x to the 5th, and y squared comes in. Y goes to the 2, and it's C7 2. Can you get the pattern here? If you look at the y power, it's the same as the number in the bottom of that combination expression there. So reduce the x power, increase the y power by 1 each time, and set up your combination expression in the front, where this is n and this is r, and r starts at 0 on the outside of Pascal's triangle. So this is C1 0, the next row C2 0, C3 0. Don't forget that R starts at 0 there. Alright, what about the expansion of 2k take 3 to the 5th, which we did before? So it's 2k to the highest power, which is 5, and we start off with C5 0. Okay, then we go to 1 less power of k and bring neg3 into the game. So it's then neg3 to the 1, and it's C5 1. Then reduce the power of 2k to the 3 there and bring in neg3 to the 2, and it's C5 2. Look at the matching. The power of that second term equals the number in the bottom here. Then you get 2k squared and neg3 cubed and C5 3. So you put all those numbers in. Now right here you could use a calculator to work out those values, or you could go to Pascal's triangle. Okay, I don't think you're going to use the definition every time. It's going to be too slow. You do have to know how to do the calculation in this new course, but I think that's going to be a bit slow to do that every time. Let's have a look at the next example. There's a few of them here. Find the term containing a cubed in this expansion. Well, a cubed is going to be what? Well, the a cubed term, if this is cubed, and they're explaining it over here, let's do it a slightly different way. If this is cubed, then neg3b, the sum of the powers must be 9, mustn't it? Has to be to the 6th. Remember, these powers always sum to n, which is 9 here. And then what's your combination out the front? It's 9 6. It's actually also equal to 9 3. Okay, and so that's what Pearson's has got here. They've used an explanation centred around this. I think I'd rather see you sussing it out with the properties of the form of that term. The sum of the powers is 9. Okay. Find the independent term of x, independent of x, the constant term. So now we might have to use the formula a bit. So here we want overall, you want just a number and x to the naught. So you want the powers of x in these two terms to come to 0 basically. So let's say we don't know what the terms are. So the first one is 4x cubed, and let's say it's 5 take I, and neg 2x squared, which is this thing here, is to the I. So the sum of these, remember, has to equal 5. So if we say let this one be I, then this one is 5 take I. Remember, we don't know what this term is, and then it's C5I. Now, if you're having a constant term, let's just get rid of that now. If you're having a constant term, we know that the overall power of x, let's do it here, the overall power of x, that first x is going to be x cubed to the 5 take I, and this other one is going to be x to the neg 2i. So the sum of those, if you don't want any x's, has to equal 0 over here. So constructing a term, this is getting a bit hard now, so therefore I must be 3. So you can then put the term back, 4x cubed 5c3, you've found the I, this is 5 take I, 5 take 3 is 2, this term to the I. And then you can work out what that constant term is. So this is a harder problem. They've always asked this in exams. They like this one. The key thing is the constant term means you must have a 0 power there, so there's no x terms. So the combo of powers must equal 0. So you've got to start off with the second term being I and the first term being n take I. And then you work out your overall power of the x term in there, and the sum has to be 0. That's the idea. See if you can study that and see what's going on there. Let's have a look at, I think this is the final example. Can find the coefficient of b to the 6. Uh-oh, there are 2 b terms. So let's do the same thing again. Let's call this one, this is neg b to the neg 1, if you like. And so here let that be I, so there's neg 1 on b, raise that to the I. So the other term must be raised to the 12 take I. Remember, the sum equals n, which here is 12. And the missing number out the front is C12I. Now what are we doing here? Well, let's look at the power of b. Here, it's b squared to the 12 take I, and this one. And we want that overall power to come to a 6, because we wanted b to the 6. So what must I be, so that when those two terms combine, your overall power is 6? So I would go away and do it over here. This is b to the 2 by 12 take I, and this is b, neg b to the neg 1 to the I. So let's combine the powers. This is 24 take 2i, and this one is take 1i, that's 24 take 3i, and that has to equal 6. So neg 3i equals neg 18. I has to equal 6. So there, that's what they've done down here, plucking out the terms. Now you've got to put the whole thing together. So if I equals 6, the number out the front, C12, 6, and then it's 2b squared to the 12 take I, so it's 12 take I is 6, and then the b squared by the other term is going to give -1, and so you get your constant. Well, we can go back up here and work it all out again with I equals 6 in there, looking at each term and just showing that they come to b to the 6 there. Okay, so that's the coefficient. So this would be the term 59136 b to the 6. Okay, so in here you will have your powers of b worked out. b to the 24 take 18 is b to the 6. So you're trying to cancel them down, if you like, the b terms, to get a particular value. So that's going to need some practice. All right, let's have some practice then. Here we are. Here are the problems, 3 through 10. So I might like to pause that. It's important to go through all of these problems, I think. Extremely important. Remember, Pascal's triangle can be replaced by combination expressions and keep the pattern of the expansion, pattern of terms, correct, so that you can track them through and to get the right number of each term. If it's a small one, you might just use Pascal's triangle. If it's a bigger one, you might go straight to the line by using this, and probably you'd use it on the calculator, unless otherwise asked to do it in full, in which case we'd have to remember that we've got this one, and this could be in paper 1, of course, where you don't have the use of a calculator. So you have to do it by hand. All right, have a go. I'll take you down to the solutions now. There's quite a few of these now as part of question 3 down to C. A lot of working out there. Let's go then down to the next little section there, E, F, G, H. I, J, K. That's going through all those terms there. Then we've got question 4. 4 through 7 will fit on there. And then 8, 9 and 10. So there they all are. A fair bit of work, some interesting little calculations there. But see what you make of it. Now that completes the last item in topic 1 in the new syllabus. So it's cheers for now from me. Keep working hard.